Hi everyone. So today we will be continuing talking about some basic properties about linear transformations on inner product spaces. In the past 2 weeks, we have been learning the properties about self-adjoint linear transformations and unitary linear transformation on linear product. Let us basically recall its definition. We start from vector space with an inner product on it of a fixed field. Say F equals the field of real numbers or the field of complex numbers. And on this inner space, inner product space, we consider a linear transformation T. And by this representation, it admits an adjoint map, which is defined by T star. That is a unit operator satisfying the following property. Say, the inner product of alpha with T beta equal to the inner product of T star alpha with beta for any alpha beta in V. So many basic properties of T can be studied via studying T star. For example, we call that linear transformation T is self-adjoint if it coincides with its adjoint. And we call that T is unitary if its inverse is equal to its transpose, its self-adjoint. And we also know that the matrix representation of an adjoint map is just the complex conjugate transpose of the original one. Today, we are going to study a more general family of linear transformations on the inner product space, which is called normal. Okay. I guess some of you may have been familiar with this notion. Say, let's call a linear transformation to be normal if T commutes with its adjoint. Say, the composition of T with T star just equals T star composition with T. Yeah. Okay. So this definition can be made either over the field of real numbers or over the field of complex numbers. But for the sake of convenience, we will first focus on the complex inner product space case. Okay. So let me state criterion for a linear transformation to be a normal one on a complex inner product space. Okay. So let T be a linear transformation over a complex vector space. Then the following are equivalent. First, okay, T is normal. The second statement is that any T invariant subspace any orthogonal complement, the orthogonal complement of any T invariant subspace is also T invariant. And the third one, any T invariant subspace is also invariant on the T star, which is its joint. if T admits an eigenvector, say alpha, belonging to the eigenvalue C, then it is also an eigenvector of T star with the eigenvalue conjugate of C. Okay. And the fifth one means that under some suitable basis of V, which is orthonormal basis, of course, the matrix representation of our linear transformation T is a diagonal one. Okay. We will first prove that the five statements here are actually equivalent to each other. Okay. Okay. I wish I made all this clear. We will follow the lines that the fifth implies the first and the second and the third and the fourth, and finally to the fifth. Okay. So 5 implies 1 means that, okay, if there exists an orthonormal basis of B or V such that with respect to this base our matrix representation is diagonal, then we may check the normality of this linear transformation just under this basis. So, since it's a diagonal matrix, must commute with its adjoint. So, the normality is easily checked here. Okay. Second is to check 1 implies 2. Means that if T is normal, okay, T is normal. Okay. Then it means that there exists an orthonormal basis of B. With respect to which the matrix representation of T is a normal matrix. Now we are going to consider any T invariant subspace. It means that, okay, we can make we can take this orthonormal basis B as follows. We take the first, say, K orthonormal vectors as the orthonormal basis of this T invariant subspace W, and then extend it to a complete basis of the whole space B. Then under this special chosen basis, our matrix representation will be of the broad upper triangular form. Okay. Here let W be a T invariant, and B holds with basis from W and basis from the orthogonal complement, the W per. We will have the matrix representation is of the form A11, A12, and the A21 is 0, A22. Okay. Then we should check the normality of this matrix. Okay. Okay. Let me call it as A, capital A here. So from the and we also know that under the same set of basis, the T star has a matrix representation of A conjugate transpose, which is just A11 conjugate transpose, A12 conjugate transpose, 0, A22 conjugate transpose. Okay. Then we check the condition that A commutes with its conjugate transpose, since it's normal. Okay. So we directly compute the matrix. Okay. A11. Okay, choose times this one. Should equal A11. Okay, transpose. Okay, that's fine. So this is a matrix equation, and we should extract some useful information from this. For example, we may look at the first line, the first row with the first column, say, and the left-hand side equals A11 times A11 conjugate transpose plus A12 conjugate transpose, and the right-hand side just equals A11 conjugate transpose times A11. Okay. So there are two terms on the left-hand side, but one on the right. Yeah, and we should say it gives some information from this. So if I claim that this extra term here should be 0, why? Okay, let me explain it. A12 times A12 conjugate transpose is 0. Why? Okay, so the advantage of finite dimensional vector space here is that we could take the trace of both sides. Taking the trace. This gives that, okay, the trace of A11 conjugate transpose plus trace of A12 conjugate transpose equals the trace of A11 conjugate transpose with times A11. Okay. And we know that trace AB always equals to trace BA. So these terms are equal, which implies that the middle term should be 0. But you know what is the matrix entries in matrix times with its conjugate transpose? Ij just equals the sum of k from 1 to n, and aik. The square of it is the modulus of aik from k from 1 to n. So this term is 0. The trace is 0 means that each summation here should be 0. Okay, to write I here, yeah, right? All these are 0. So, in particular, this calculation implies that our A11 matrix that lies on the upper left corner inside the big one is actually a normal matrix. Okay. From the claim, we see that A11 is normal. Okay, that's a basic observation, and we see that of course A1 here we also have A12. And actually we have A12 there. So actually we will have our matrix form as a diagonal form. This means that T preserves the orthogonal complement of W. Okay. So this proof of 1 implies 2. Yeah. Okay. And this is, I should emphasize here that 1 implies 2 is the only non-trivial part of the among these equivalences. Okay. So now let's focus on 2 implies 3. Yeah. Okay. So now let W be an invariant subspace. Okay, and we are going to show that W is also invariant under T star. And how should we do that? We start with the observation that W just equals to the orthogonal complement of its orthogonal complement. So to check that an vector lies in W, it's fuzzy to check that it is perpendicular to any vector in its orthogonal complement. Yeah. So for any alpha in W, we should show that T star alpha is perpendicular to any vector in W perp. So beta in W perp. We check that the inner product of T star alpha with beta. Okay, so by definition, it just equals alpha T beta. Okay, and now, okay, since W is T invariant, then by 2 here, W T invariant implies that W perp is also T invariant. So beta in W perp implies that T beta also in W perp. That means that the inner product of alpha and the vector in W perp is 0. Okay, so this just means that T star alpha is perpendicular to any vector in W perp. Just T star alpha in W. Okay. So from any vector in W, we will get its image under the T star is also in W, which means that W is invariant on T star. Okay, so that's an easy proof from 2 to 3. And let's get the fourth, the implication from 3 to 4 is also easy. Okay, say that T alpha, let alpha be an eigenvector of T, then we may consider the one-dimensional subspace just spanned by this alpha. It is also is of course T invariant. Since alpha is an eigenvector. Then 3 just implies that okay, W is also T star invariant. Okay, since it is a one-dimensional subspace, it just means that okay, there exists another complement number C prime such that T star alpha equals T prime. Yeah, right? And finally, we should check that this C prime just coincides with our conjugate of C. So how do we do that? We just check the norm of the matrix. Okay, so check. We do the alpha. We do the inner product alpha with T star alpha. Okay, it equals T alpha with alpha in the product by definition. And the left hand side equals, okay, C prime conjugate of alpha. And the right hand side equals, okay, T alpha equals C alpha. Alpha. Okay. Since alpha is not zero, it just implies C prime equals to the complex conjugate of C. Yeah. That finishes proof of 3 implies 4. Then, what about the last one? Okay. You erase some here. Yeah. So far, we have shown that 5 implies 1, implies 2, implies 3, implies 4. Right? And now we are going to check that 4 implies 5. Okay, so since T is a linear transformation over a complex linear space, it must admit an eigenvalue and with the corresponding eigenvector. So let us make the eigenvalue of modulus 1, say alpha here. And this implies that, okay, we could always find a new vector. So, and we take an also normal basis formed by alpha and blah from alpha probe. Okay, so under this basis, our matrix representation of the form C and 0 here, and a star here, and a gray star here. Okay, but now we know that, okay, on the same set of base element, our matrix representation of T star is obviously conjugate form, is a conjugate transpose. So this form. What you see, okay, so the first base element is alpha, and the fourth condition means that alpha is always invariant under T star, which means that this star must be 0. By 4. So this easy matrix calculation just implies that, okay, T is of the form C 0, 0 here, so the diagonal, the quasi-diagonal form, and we just do induction on dimension, and we could conclude that, okay, finally T will be of the diagonal form. So this finishes our proof of these 5 statements. That will be very nice. Okay. And the only thing that I would like to emphasize here is that, okay, the proof here from 5 to 1 to 2 to 3 to 4 also holds not only for C, but also for R, the field of real numbers. But the last implication from 4 to 5, since we need to take an eigenvalue and then a corresponding eigenvector of T first, so it should depend on whether the characteristic of polynomial of this linear transformation has a root over this field, and this is not always true if we are considering the field of real numbers. So here is a remark that about the real case. So if we replace C by R here, then all these statements are equivalent except the last one, and the last one underneath the multiplication, say 5 prime here, is that there exists an orthonormal basis P of V such that the matrix representation is of the block diagonal form. Block diagonal form, and each diagonal block is of order less than 2, or less than not exceeding 2. This is because the only irreducible real coefficient polynomials are of the degree 1 or 2.
Okay. In the real case, 5 is equivalent to that T is self-adjoint, isn't it?
Oh, yeah, that's a good point. Yeah. So, Yao just means that, okay, if we insist on the real case with the condition 5, then, yeah, T with the condition 5 is equivalent, according to our preceding discussions about the self-adjoint maps. T is self-adjoint. Okay. And it in particular means that any values of a self-adjoint map must be real. Okay. That's very good. Excellent. So now I'm going to discuss some applications of this theorem about criterions of a normal operator. Okay, so let's just write it as a corollaries. Okay, one. Okay, if there exists, say, our inner product subspaces also over C, and we are given two linear operators, say T and S, on V, such that they commute with each other, and T is normal. Then the conclusion is that S also commutes with the adjoint of T. To simply put it, if a linear operator commutes with a normal operator, then it also commutes with the adjoint of it. Okay. So that will be a simple corollary of our equivalence from 1 to 5. Since, okay, under some suitable basis, we may assume that the matrix of representation of our T is the normal, is of the diagonal form. Okay, so let's just write T to the matrix, diagonal one. Okay, so diagonal, say A1, A, and write the matrix representation under the same set of basis of S as matrix B here. Okay, then the commuting relation is just imply that, okay, if we examine the value, the matrix entry I at the ij, then we will get AI times Bij equals Bij Aj. Okay, right? The left multiplication by a diagonal matrix is just to multiply the ith coordinate to the ith row, and the right multiplication by a diagonal one is just to multiply the jth column by the jth coordinate. Okay, so from this equation we see that, okay, either AI equals Aj or Bij is 0. These are the two only possibilities. But from either case, we will deduce that AI conjugate times Bij equals Bij Aj conjugate. Yeah. Then if already AI equals Aj, then of course AI bar equals Aj bar, then this equation will hold. And if Bij is 0, this equation is even true. But this simple observation just means that, okay, since our T side is the conjugate of this diagonal matrix, this just means that T star goes with S is just S goes with T star. Okay, so this finishes the proof of corollary 1. Okay. And I would also like to mention another variant of this corollary, corollary 2, which is seemingly stronger than the preceding one, but actually equivalent. So, still under the same assumption, this is the inner product space over the field of complex numbers, but now the linear operator the linear operator S not only commute with T, but just intertwines the action of T1 and T2. Okay, it satisfies that T1 comes with S equals S comes with T2. Okay, and we should assume that now T1 T2 are both normal. So the natural expectation is that S also intertwines the action of T1 star with and T2 star. So it seems to be stronger than the first one. But I would like to show you a matrix technique, or sometimes called a matrix trick, from correlate 1 to 2. Say, we consider linear operator on the product space by increasing the dimension. Put T1, T2 on the diagonal. Okay, so it is a normal matrix on the product, still normal. And we put S tilde to be 0, S, 0, 0. We put S on the upper right corner. Then, okay, on this vector space V times V, it is ready to check that T tilde composed with S tilde is equal to S tilde composed with T tilde. Okay, because of this equation. And by corollary 1, we just say that, okay, T tilde star composed with S tilde. And this equation is just equivalent to that, okay, T1 star composed with S plus S composed with T2 star. Okay, so this is important corollary from our criterion, which is sometimes called the Linear theorem. Okay. And I would like to give you more variants of this theorem, and maybe its proof is just left as an exercise. So variant. Okay. So still we are working on a complex in the product space, and we should have some T, T1, T2 as these three linear transformations with the condition that, okay, this intertwining one and S is normal here. Okay, so question 1, is this guarantee that S intertwines with the actions of T1 star and T2 star? Okay, so here we change the condition from, okay, T1, T2 being normal to S being normal. Okay. And the second one is that, okay, we consider more conditions here. Okay, T1, S intertwines the action of T1 and T2, and also intertwines the action of T2 and T1. Okay. In the following sense. And S is normal. So, if this implies that intertwines the action of T1 star and T2 star, also intertwines with the action of T2 star and T1 star. Okay. And homework is to check these two facts and show that, okay, 1 is false, but 2 is true. Okay. So you see, this is different from the situation that you have seen in the Fugler theorem. And we should pause here. Okay. Thank you for listening.